Good morning, students. I was waiting for some more students to join, but before it becomes too late, let us start the class. Finally, it is the people who join the class are more important. We need not wait for the people who are yet to join. So today's experiment is differential amplifier. A differential amplifier is a type of electronic amplifier that amplifies the difference between two input voltages but suppresses any voltage common to the two inputs. You'll have to revise some of your learnings which you had in the 4th semester in the linear integrated circuits, because that is where you studied operational amplifier in detail. So it is an analog circuit with two inputs V plus and V minus and one output V out, in which the output is ideally proportional to the difference between the two voltages. V out is equal to A into V plus minus V minus, where A is the gain of the amplifier. These are the dimensions of the devices. Let me show you the circuit diagram directly. You can see this circuit diagram now. Now, here we have two devices. There is this V1 here, there is this V2 here. You can see this. Let me annotate. You have this one input V1, one more input V2. And then there is this VSS and there is this VDD, as we have been using only VSS and VDD in the previous experiments as well. Now below you can see an NMOS transistor, and it is connected to one more NMOS with the gate and drain shorted. You already know that when gate and drain are shorted, VGS is equal to VDS. When VGS is equal to VDS, we are keeping the transistor only in the saturation region and we will not allow it to get into the linear region. That means the transistor will not be completely trying to turn on. As long as VGS is there, VGS has to be greater than VT for the transistor to turn on. Now VDS cannot become less than VT also. If the transistor has to come into linear region, VDS has to become less than VT. Ideally, VDS has to be 0. But in the case when we short gate and drain, we are preventing the transistor to completely turn on. So in that case, this particular transistor is always in the saturation region. Now there is this IDC given. So that IDC we fix a value for the current source. Later on I will show you. Now when we fix a value of current here, imagine this is the current coming into the transistor, and because it cannot go into the linear region as it is in the saturation region, you know that in the saturation region the current is going to remain constant. So that way this particular device is going to be working in saturation region as a current source. Now this gate and this gate are connected here. When this gate and this gate are connected here, this VGS is same as this VGS. And you know that in the saturation region, IDS is equal to mu n into Cox into VGS minus VT whole squared by 2. If mu n and Cox and W and L, if they are all same for both of these transistors, then even VT, it is the same process there now. So even VT is same, dimensions are same. That means the current is proportional only to VGS now, because IDS is equal to mu n into Cox into W by L into VGS minus VT whole squared by 2. Now when all other things are common to both of these devices, then if VGS is also common now, gate is shorted, even the VGS is common now. So whatever is the current flowing here, that will be the same current here. That means the current, whatever IDC we give, we are forcing the right side NMOS to carry only that much of current. So now this concept is called current mirroring. You have already studied it in the theory classes, still I am revising it. This method is called current mirroring method. Now the advantage here is, this NMOS we are using with respect to the left side NMOS, and left side NMOS we are using as a current source, and gates we are shorting, by means of which we can control the current which is flowing through the right side NMOS by using the left side NMOS. We decide the current that will flow through the right side NMOS also. For example, let us say 1 milliampere here. Just for an example, let us say this current is 1 milliampere. Now naturally this current is also 1 milliampere. Let us assume that right now. Now you can see at the top, we have one amplifying transistor here, and we have one more amplifying transistor here. Later on we will come to V1 and V2. Now as we have seen in the common source amplifier, instead of a resistor we use a transistor for working as a resistor in the linear region. So now this input V1 is connected to a common source amplifier. Its source is connected to the biasing transistor below. And at the right side also you can see this V2 is connected to one more common source amplifier only. Source is shorted there. Both sources are shorted. And input is given at the gate, output is taken here at the drain. So it is a common source amplifier. Now in this common source amplifier, at the top there is a resistor required. Now we already know that instead of resistors we are using Cmos devices here. You can see at the top there, even for this PMOS device, this particular PMOS device, you can see the gate and the drain are shorted. When the gate and the drain are shorted, the PMOS device is going to work in saturation. We are preventing its linear operation, means we are preventing it to completely turn on. And gate are shorted here, and here this source and source are connected to VDD. That means the VGS of the left side PMOS is same as the VGS of the right side PMOS. In that way, whatever is the current flowing through this PMOS, it will be the same current flowing through this PMOS. Because now the left side PMOS is working like a current source, and the right side PMOS is connected through a current mirroring concept. Because the gate are shorted, gate source voltage is same for both of them. All other dimensions are also same. You can observe here that the upper PMOS is connected and its width is 15 micrometer. Whereas the amplifying NMOS is having a width 3 micrometer. And the biasing transistor below is having a width 4.5 micrometer. They are all related that way. Length is 1 micron everywhere for all these devices. So if we fix IDC here as 1 milliampere, the same current has to flow through this NMOS, biasing transistor. Now as there are two branches here, as the two branches are identical, now the current that can flow through the left side PMOS has to be 0.5 milliampere, and for the right side PMOS it has to be 0.5 milliampere. Why? Because the two branches are identical and the two sources are connected here to the biasing transistor. So by means of fixing this current IDC, we are deciding what amount of current has to flow through the amplifying transistors also. I hope it is clear. If you have any questions, you can ask. Otherwise, I will stop annotating and I will proceed for discussing the differential amplifier now. So if there are no more questions, let me proceed. Okay. So now we are sure here it is 1 milliampere. Later the values may change. I am just giving an example of 1 milliampere. Here it is 1 milliampere. Here it is 1 milliampere. Now let me zoom in. Let us ignore the lower part of the circuit. Let us only focus on the upper part of the circuit. Now this is the differential amplifier, and let me write the symbol for differential amplifier. This is the symbol for differential amplifier. Actually, inside the operational amplifier, there will be a differential amplifier, then there will be a middle gain stage, and then there is a high gain stage at the end. In general, operational amplifier can be 2-stage or 3-stage, sometimes 4-stage also. So the differential amplifier is going to amplify the difference between the two inputs V1 and V2. And typically we can say that the gain of the differential amplifier is A, the open loop gain. It will be, in general, the open loop gain will be very high. We connect one feedback resistor as a negative feedback to reduce the gain. In case of an op amp, you know that. But in case of a differential amplifier, we need not assume that the gain is infinity. We need not assume that way because we are dealing with a single stage amplifier now. So now I have a question to you. Out of this V1 and V2, which one is inverting input? We have this V1, and we have this V2. Which one is inverting input? Which one is non-inverting input with respect to this particular configuration? Students have to answer. People are listening to me? There are 8 students in the class. Are they listening to me? Kuldeep says yes, sir. Then answer my question. Out of V1 and V2, which one is inverting input, which one is non-inverting input? Even if you are wrong, no problem. I will correct it later on. Okay. One student has written negative sign is inverting input. Yeah, that I know. My question is not that. Negative sign is inverting input, that I know. Whether V1 is inverting input, V2 is inverting input, as with reference to circuit diagram. That is what I wanted. Okay, Kuldeep is telling, I guess V1 is negative. Yeah, he is guessing. Now let us see. In engineering and in technology, we cannot guess things. Let us see now. I'll help you in understanding this circuit. Let me write the waveform here now. Let me write an input waveform here, V1. And let us say we connect this V2 to ground. Let us say we are connecting the V2 to VSS, not ground, VSS let us say. Or even to ground, let us say it is to ground because 0 volts. Now, the right side Nmos is off, V2 we are connected to ground, V1 we have connected a AC signal. Now, as you already know, there is, in this branch, there is 0.5 milliampere flowing. as per our assumption of IDC as 1 milliampere. And in this branch now 0.5 milliamperes is flowing. 0.5 milliampere. Let me not write milli, I keep telling it. So now, both the upper PMOS are in linear region. They are working as resistors. But this NMOS, both the NMOSs, NM1 and NM0 here, corresponding to V1 and V2. Now, they cannot be in the linear region as such. Because for an amplifier to work, you know that the device must be working in the middle of the load line. The quiescent point is in the middle of the load line. So the transistor cannot be completely on, it cannot be completely off. I have been telling you that is how the device dimensions are decided. Now these N-MOSFETs corresponding to V1 and V2 both will be in the saturation region. As I keep repeatedly telling you, in case of BJT, whatever we call it as saturation, in case of MOSFET, we call it as a linear region. In case of BJT, whatever we call it as active region, we call it as saturation region in MOSFET. This should be very clear to you always. It is the two different sets of scientists who invented these devices and who worked on these devices. That is how they kept the names for the regions. In the case of BJT, saturation means the device is completely on. In the case of MOSFET, the saturation means device is half on. That is the idea here. So this NMOS and NMOS corresponding to V1 and V2 both will be in the saturation region or half on. Now we are taking the output here. Now when the gate voltage at V1 increases, now this particular NMOS is gradually moving towards linear region. From saturation it is moving towards linear region. That means the current here, let us say it increases to 0.6. Let us assume that way, it increases to 0.6. Now the current here, if it increases to 0.6, now we have seen that below current is constant as 1 milliampere. That is by means of the biasing resistor. By means of the biasing transistor, we have seen that total current is going to be constant. Now in the positive cycle, when the input voltage to the first transistor increases, it gradually moves towards saturation moves towards linear because current is proportional to VGS now. So when VGS increases, IDS increases. When IDS increases, let us say it increases to 0.6 milliampere. Now as the total current has to be constant, what should be the current here now? The current here should be 0.4 milliampere now. When this is 0.6, total it is 1 milliampere, 0.5 plus 0.5. Because of the input signal, when the current through the left side branch increases, current through the right side branch has to reduce because at the bottom, the current is 1 milliampere only. So what happens is when the current in this left branch increases, that is going to reverse bias the source and gate junction. Not junction, region we should say. When the source current of V1 increases, then it is causing a slightly turning off of the V2 transistor. Now here when the gate to source voltage is slightly being affected, it is being reverse biased by the inflow of 0.1 milliampere at the other branch. At the bottom it has to be 1 milliampere only, this manner. Total it is 1 milliampere only. Now when this left side current increases, it is opposing the right side current. That is how this V2 slightly moves towards cutoff region. And because of which current here reduces. And you know that when the device moves towards cutoff region, the voltage at the output increases. Isn't it? When the device is moving towards cutoff region, we are taking the output at the drain. This is like a switch now. When the switch is turning off, here the voltage is going to increase. So, in this way, here in the positive cycle, voltage will increase. Here when it is positive cycle, here voltage will increase. What happens in the negative cycle now? In the negative cycle, in the left side branch, the current reduces because the gate to source voltage is reduced to negative side. When the current here reduces, V1 now moves towards cutoff region. As the total current has to be same, 1 milliampere. Now, this V2 moves towards linear region and the current at the right side increases. And when current increases, when the device moves towards linear region, the device V2 is switching on towards linear region, and at the drain the voltage is going to reduce. Please remember, this is a DC circuit, it is not AC circuit. So by default we are assuming here 0. That is why we are connecting VDD and VSS there. We are connecting plus 2.5 and minus 2.5 supply voltage. Considering normally this is at 0 volts. So now V1 is the non-inverting input. This is the answer to Kuldeep's guess. Now, guess will not work in engineering and in science and technology. You will have to analyze the circuit. So V1 is the non-inverting input. So let me write V1 here. I hope this is understood. If students have any queries, you can ask me, or else I will proceed for the next inverting configuration. Is it clear now? If it is clear, put yes in the chat box. Okay. Kuldeep has put yes. So now let me proceed for discussing the inverting input. So obviously now V2 is the inverting input. V1 is the non-inverting input. V2 is the inverting input. Now because we have grounded V2, whatever input we gave at V1, that is only going to be amplified, because the difference between V1 and V2 will be V1 only. Now let us do the other thing. Let us ground V1 now. And let us give input to V2 now. So, now you already know the current through both PMOSes are going to be equal when the input signal is absent. And let us assume output is at 0 volts now. And both these N MOSFETs are working in the saturation region or in the quiescent point in the middle of the load line. Now when we apply the positive cycle, V2 will turn on now. When V2 is turning on, let us say this is going to become 0.6 now in the positive cycle. Now here at the other end, the other thing will happen. This will become 0.4 now. This will become 0.4. Let me write it cleanly. Okay. This is now 0.4. So, when this V2 goes towards linear region, at the drain, the voltage is going to reduce. So, now the output will be like this. When this V2 goes towards linear region, the voltage at the drain is going to reduce, and because the net current is always same, so at the other side, the voltage is going to increase. But anyhow, we are not considering the other side. Current is reducing here, voltage will be increasing there. Here current is increasing, voltage will be reducing. Similarly, in the negative cycle, the transistor corresponding to V2 is gradually going towards cutoff region from the saturation region, and due to which here the voltage is going to increase. So this way V2 is going to be the inverting input. Now you can see when the input is applied to V2, correspondingly output is having a 180 degree phase shift with the input. That way now V1 is the non-inverting input, V2 is going to be the inverting input. Now my question is, let us say we do not take output here. If we take output here, let us say we are taking output here, then what is the change going to happen? Let us say instead of taking output at the right side of the amplifier's branch, let us take output at the right side, left side of the amplifier's branch. What is the change going to happen? Anybody can tell me? Can anybody tell me? Instead of taking output at the right side branch, if we take output at the left side branch, in what way it will change? Yeah, Kuldeep says the answer, V2 becomes non-inverting, right? At that time, V2 is going to become a non-inverting input, V1 is going to become a inverting input. Now my next question, if we take both outputs, then what is going to happen? If we take both outputs, then what is going to happen? We will have two inputs, we will have two outputs. Can we take it that way? Let me try to help you. Let me write the differential amplifier symbol now. This is the symbol I am writing. Earlier we took, let me change the color there. Earlier we took the output here. Okay. Earlier we took the output here. I am purposefully writing a different color. Now let me write like this. Like this. And let me remove this one. So now you can see there are two inputs, there are two outputs. We are taking both the outputs. Input is differential input. Output is also differential output. In the earlier case, in whatever we studied operational amplifier, it was having two inputs and one output. Now that is called as a single-ended output. Means at the output you will have the signal with respect to ground. But now in this case, as we are taking both outputs, now this is a differential input and differential output. And if the inputs are like minus and plus here, outputs will be plus and minus here, because they will have a complementary phase there. Now this is like a differential input, differential output amplifier, if we take both the outputs. Now can you tell me what is the advantage of differential input and differential output amplifier? Because we always know that differential amplifier is amplifying the difference of two signals, and the difference is amplified and we are getting it as single-ended output with respect to ground. But now in this particular case, there is input also differential, output also differential. What may be the advantage here? Any answers? gain is double. No, gain will not be double. Gain is A into V plus minus V minus, right? Gain is always the difference between two inputs is going to be amplified. That gain is fixed now. Gain depends on the dimensions of the devices here or based on the current here. Gain of the total circuit is fixed. Only thing is we are taking a different arrangement for output. We are taking output in a different style here. Gain will not become double. Only thing was earlier the output was with respect to ground. Now the output is with respect to each other because the output is also differential. There is some other serious advantage, one great advantage. Whenever you think of op-amp, you think of some terms. Which is that term which you immediately remember whenever you think of op-amp? There are two terms in op-amp's discussion itself. CMRR and PSRR. Common mode rejection ratio and power supply rejection ratio. Now when you have differential input, differential output amplifier, this will have a much larger CMRR. It will have a much larger common mode rejection ratio. Can you tell me how? I gave you a clue now that this particular circuit will have a much larger CMRR. But how it can have larger CMRR? Can anybody tell me? Okay, the answer is input is also differential, output is also differential. Noise will always be common. There is nothing called differential noise because noise is a random occurrence. Signals can have phase relationships. Noise will not be having such phase relationship because noise is an unpredictable signal occurring in the channel or in the nature or in the atmosphere, in whichever way. So, if noise occurs here, noise is going to affect both of them, both the inputs. Now, inputs are differential, outputs are also differential, which means even if the common mode noise is amplified, at the output, noise will be still reduced because output also taken as differential now. That is how differential input, differential output amplifier will have much larger common mode rejection ratio. This is especially a highly useful concept in the case of preamplifiers. For example, in your mobile phone, from the antenna, when the signal is picked up into the circuitry, in the PCB, there will be a patch antenna. And the patch antenna is going to pick up the radio frequency, 2.4 gigahertz carrier wave in a 3G phone. Now, immediately after the antenna, you will have a preamplifier for RF signal now. Now, in the atmosphere, there is many noises. There are many types of noises. I hope you recall whatever you studied in the course Analog Communication, where there is an exclusive chapter on noise itself. So, all those noises, when they get into the antenna, all these noises are random occurrences. They commonly affect both the inputs, let us say. Now, if this dual input and dual output amplifier is there as a preamplifier, there will be very less noise amplification, and later on to the same dual input, dual output amplifier, we can connect one more op-amp, one more amplifier now, like this. Now, later on we can have a single-ended output. We are connecting one dual input, dual output amplifier so as to have minimum noise amplification, so as to have only signal amplification. Later on, we can have a single-ended amplifier at the output. That is why many times amplifiers are multi-stage. They are not single-stage amplifier. Now that is the advantage of taking both outputs. Now when you simulate this circuit later on, maybe when the offline lab starts, or maybe later on, you need not blame on the pandemic that you are unable to practice in the labs. You are anyhow going to come back to college. So even in the next semester also, you can work more in the VLSI lab. In your free time or spare time, you can work more in the VLSI lab. And you can verify all these functionalities. Those who are interested to work on VLSI, they can use your spare time. You can use your spare time in practicing all these experiments again in cadence. You are going to be still there for 3 more semesters in our college, right? You still have enough time to practice if you want to practice. Now, as I have been suggesting to you earlier, those who are having keen interest in working on VLSI domain, you can take up some mini project based on the differential amplifier itself. You can actually design your own operational amplifier as a mini project in the next semester. Because you are going to study a course called microelectronics in the next semester, where you will study more about all these design aspects of the circuit. How the device dimensions are going to be decided, you are going to study in detail. So when you study in detail, instead of depending on the design values which we are giving you here, you can design your own operational amplifier for let us say a set gain of 100 dB or 120 dB or 140 dB, and for a larger bandwidth also. You can fix a bandwidth, you can fix a gain, you can design your own operational amplifier, you can only do its layout, you can project it as your accomplishment in a mini project. Later on, if required, when you come to final year, you can take up this design itself seriously and you can design an RF amplifier. Even now people are working heavily on RF amplifier having a higher gain and higher bandwidth. You know that in the case of MOSFET, as we have a lot of parasitic capacitances, obtaining a larger bandwidth is a challenge with the MOSFETs. Now people keep on trying out to get larger bandwidth and larger gains, larger stability with the amplifiers. So you can refer to the latest research papers that are being published in IEEE or in some other domains, and you can design your own operational amplifier. That is my suggestion for you. Okay, now let me proceed further with today's experiment only. Today's experiment is only this: single-ended output, dual input, and I have explained you in detail about how the circuit is working. Let us proceed now. After this circuit diagrams editing, you are going to do this editing in Virtuoso tool. Afterwards, you can make all these connections, connect VDD VSS, then you can create a symbol for the differential amplifier. You can see that default symbol that is available here. Tool generally gives a default box, rectangular box, because when you make a circuit diagram, you are giving the pins, and for the pins you are giving the directions as input and output. Based on that, the tool will give you a default rectangular box. If you want, you can create a differential amplifier symbol only, exactly, by deleting this box and keeping the pins. That is your choice again. Here it is shown as a default box. Otherwise, you can actually create the symbol for the differential amplifier as I had showed you earlier. Now connect IDC as 30 microampere. For this design, we are fixing the DC current as 30 microampere. So naturally, the two branches will have 15 microamperes each. After that, you can connect, I think you can see this screen where you can connect VDD and VSS supply voltages 2.5 volts plus and 2.5 volts minus to the same differential amplifier. Yeah, now you can see it clearly. To the same differential amplifier, you can connect the supply voltage and you can connect 30 microampere to the IDC pin. And you can connect sinusoidal input wave to V1. V1 is now non-inverting input. And you can connect a ground to the inverting input. V2 is the inverting input for our present configuration. Now we can perform transient analysis, DC analysis and AC analysis. And you can see this now. Output you can see here. I hope you can see it now clearly. This is a non-inverting amplifier with V1 as input. You can see the transient analysis here, where input is shown at the bottom. That is a very minute wave. Let us say we give 1 millivolt here. We have a large gain here because of 2 N MOSFETs now. Differential amplifier will have larger gain when compared to the previous amplifiers we discussed. So you can see, we give 1 millivolt input. You can see in the AC response as it is 100. It is slightly more than 100 also. So for a 1 millivolt input, you are getting a 100 millivolts output, which means 20 log of V0 by Vi. 20 log of 100 by 1. 20 log of 100. Log of 100 is 2. So it is a 40 dB gain. This amplifier is giving 40 decibels voltage gain because the gain is 100 times. But you can see the bandwidth here. Let me zoom in to discuss the bandwidth. Yeah. Now the gain is 100, let us say, or 40 dB. Now from 100, we have to come down to 0.7 of 100. That means we have to come down to 70. Let me take it as approximately as this point, because anyhow it is slightly more than 100 here. So let me take it as this point only, approximately. Now when we take that point, go down from that point. From this 75, let us go down. And you can see around 10 power 7. We can take it as 10 power 7 only. Or approximately, it is here it is 1 mega. 10 power 6 is 1 mega. 2, 3, 4, 5, 6, 7, 8. We can approximately take it that way as 8. So it is 8 megahertz because 10 power 7 is 10 megahertz. 8 megahertz is the bandwidth of this particular amplifier. Gain is 40 dB and it is 8 megahertz. That means what is GBP now? GBP or gain bandwidth product for the amplifier is now 40 dB is the gain into 8 megahertz is the bandwidth. So it is 320 mega is the gain bandwidth product. 8 megahertz is the bandwidth and 40 dB is the gain. So in terms of dB, I am telling the gain bandwidth product is 320 mega. We want always the gain bandwidth product which is much larger in the case of our RF amplifiers. Now you can see that here the bandwidth is only 8 megahertz. 8 megahertz is really a very less bandwidth for us. We cannot use it for high-end RF applications. Right now we are working with gigahertz and here the bandwidth is only 8 megahertz, not even 10 megahertz, even though the gain is 40 dB. Now if you want to increase the gain, you will have to compromise on the bandwidth. Right, let us say if you want to have a 80 dB gain. Right now this amplifier is having 100 times gain. If at all we want to use it as a pre-amplifier for a satellite signal, now the gain of 40 dB is nothing there. We should have a multi-stage pre-amplifier in such cases. Now think about how GPS is working. I keep telling to the students that Transistor is the 8th wonder of the world. Mobile phone is the 9th wonder of the world. Google Earth is the 10th wonder of the world. Because there are 21 plus 3, totally 24 satellites in the middle Earth orbit. They are sending these signals to the Earth. And by means of that, by means of an algorithm called a triangulation algorithm, the location is obtained. And through that location identity, each location is transmitted to you, and you simply see that in the Google Maps. It is such a wonderful application. In the Google Maps, you are able to see so many places and so many routes, so many connections, just by means of your mobile application of Google Maps. That's a very wonderful application. Now think about the base stations are receiving the GPS signal. To your mobile phone, anyhow the GPS signal is provided by means of the base stations. But the base stations have to be having the signals from the satellites that way. Now from the satellites, when the signals are received, 40 dB gain is nothing there. 40 dB gain is not at all sufficient there. So when we want to have a larger gain, we also want to have a larger bandwidth. There is a challenge here now, where 320 mega gain bandwidth product is not at all sufficient. But we know that in the case of MOSFETs, there is a lot of parasitic capacitance. And how do we increase the bandwidth? In the case of MOSFET, that is the challenge. That is where we use BJT also. We have a technology called Cmos, bipolar as well as Cmos. Now bipolar can give us a larger gain, it can give us a larger bandwidth when compared to MOSFETs. Because in the case of a BJT, the parasitic capacitances are lesser in their value when compared to MOSFET. That is because MOSFET by itself is a field effect transistor, and there it is a voltage control device. So naturally at the gate there is voltage, there is no current. But BJT is a current control device, there is a PN junction, due to which in the case of BJT the capacitance can be lesser and even the gain can be more because it is having a beta. Whereas in MOSFET it is GM or transconductance. So these are the challenges. That is when we have a technology called BiCMOS, bipolar and CMOS together, BJT and MOSFET together. Okay, that is the discussion about gain bandwidth product. Let me zoom out now to show you the other curve called transfer curve. You have at the left side you are seeing the transient analysis. In the middle now we saw the AC analysis. At the right side now you can see the DC analysis. Now in the DC analysis you can observe here. You can observe here in the DC analysis that when the input is rising from minus 2.5 to plus 2.5, output also is rising. That means there is no phase shift. But there is a change in the rise of the output. It is not completely linear that way. Because we are performing DC analysis, we are applying the input from minus 2.5 to plus 2.5 DC. Gradually we are measuring the output. Now it is following the same direction, but it is crossing over here somewhere. Near origin it is crossing over. Somewhere here it is crossing over. But we are operating this amplifier in this region only. We are operating this amplifier as a small signal amplifier. We are applying only a signal of 1 millivolt. So we are operating this transistor only in this region. This is the quiescent point for us. Whereas we can see above certain DC value, there is a complete linear operation here for the transistors. This was a complete cutoff operation for the transistors. So our Q point is exactly at 0 itself. That is how the circuit is designed. Now this curve indicates that it is a non-inverting amplifier, because as input is increasing, output is also following the same pattern, same direction. That is the verification from the DC analysis now. So let us proceed further. I have shown you all the three analyses. You can measure the gain and the bandwidth. You can plot the phase curve and the gain curve also. Now you can see upper one is the phase curve, where you can see it is now 0 degree. And the gain curve, you can see it is approximately 40 dB, whatever I had told earlier. It is about 40 dB. Now from 40 dB, you come to around 37 dB, and at that 37 dB, measure the bandwidth, measure the frequency. This is now a direct coupled amplifier, because at the input there are no coupling capacitances connected, unlike BJT. In BJT, we need coupling capacitances. But in MOSFETs, we don't require coupling capacitances, because they already have capacitances as gate capacitances. And there is no gate current at all. So that way, you can see this is a direct coupled amplifier, where at the lower frequency, you don't have a cutoff frequency at all. Only at the higher frequency, you have a cutoff frequency. So this is the phase and gain plot. Again, I had told you about the phase margin and the gain margin. You can see here, there is sufficient phase margin and gain margin. Whenever the gain is becoming 0, the phase should not become minus 180 at that time. That is the point there. You can extend this 10 power 8 to 10 power 10 also, 10 power 12 also, while performing the simulation of this experiment. And you can actually measure the gain margin and phase margin also. Those students who are interested in understanding all these basics, you can actually verify all these things. Now with the inverting amplifier, you can see, let me zoom in. With the inverting amplifier, you can see with the input signal there is an inversion, but as input signal is only 1 millivolt, output signal is a larger amplitude, 100 times is the gain. You are unable to see the complete input here. That is fine. Anyhow, there is going to be 180 degree phase shift. Now you can see the gain also remains the same, 100 dB, and you can see the bandwidth also remains the same, because all the dimensions of the devices are the same. Now you can see here, when the input is going from minus 2.5 to plus 2.5, output was initially at plus 2.5, now it is coming down, and we are operating the amplifier here only. Near 0 only we are operating, that is the Q point for us. So you need not worry about this particular portion or this particular portion. In this portion, when the input was minus 2.5, the transistor was in the cutoff region. So we were getting plus 2.5. Now it is coming down here, but it is not going to minus 2.5, because at the top we have those two resistors. As they are working as resistors, there is always a DC voltage drop across them. That is how it is working like this. Now if you want it to come down here, then you have to go for an op-amp only, which means op-amp should have a larger DC gain also. Right now we are working only with the DC differential amplifier. You have to connect one more amplifier at the output, where you should give a larger gain. When you give a larger gain, automatically this line comes down here. Otherwise, you can verify that in the DC analysis, output and input are out of phase. When input is increasing, output is reducing. That way, this particular input is the inverting input. So after this simulation, you can proceed for the layout. I am showing you the layout directly here. This is the layout now, where you can see two P MOSFETs at the top with body bias. You can connect here, see here. We already know that for every 10 micron, we have to connect on via, and through that via, we have to connect the body to VDD. That is done here. Uppermost metal track is VDD, and you can see the body is connected to VDD. Then the source of both the P MOSFETs is connected to VDD. Left side is taken as the source, and the right side is drain. The drain of this first P MOSFET is connected to the drain of NMOS below. You can see here. And these are the two amplifying transistors. The smaller ones are the two NMOSFETs, which are the amplifying transistors. And you can see to both of the gates, V1 and V2 are connected. These are V1 and V2. And the source of left side NMOS and the right side NMOS, they are connected together. They are connected to the drain of the biasing transistor. This right side NMOS is the biasing transistor. And its source is connected to VSS. Lowermost one is VSS. Similarly, we have this current source at the left side, that is the NMOS. This is the IDC point here. And you can see the IDC is connected to the drain also, to the gate also, because gate and drain are shorted there. Now the shorting is done by means of one more via. Poly to metal 1, M1 to poly via is there here. And you can see these vias, these are M1 to N-well vias. And you can see one via here, this is M1 to P sub via. Now the body of N-MOSFET should be connected to VSS. But here, as these devices are only 3 micrometer and 4.5 micrometer, only one via is enough here. Because all these 4 devices are very much nearer to this particular via. The rule here is that for every 10 micron, there must be a via. But this gap does not increase 10 micron. You can put a scale also and you can find out. So one via is sufficient here, that is connected to VSS. And here also you can see one more via. This via is for these 2 transistors, this via is for these 2 biasing transistors. And at the top you can see the gate and drain are again shorted here also for the left side PMOS. And you can see one via here, metal to poly via. And the same gate is connected to the other right side PMOS because gate to gate are shorted there. Here also gate to gate are shorted for N-MOSFETs. Now you can see in the layout that always polysilicon can move over metal wire. We can easily cross over. Let me zoom in and let me show you. You can see here metal line is there, poly line is there. Poly and metal can always cross over, no problem at all. Because poly is a lower layer, metal is a upper layer. In between them there will be a field oxide layer. So no problem at all. We can make connections like this. Only thing is, if there are 2 metal paths, metal to metal should not go. If there are 2 different poly paths, poly to poly also should not go because they are the same layer. Otherwise, metal can always cross over poly. That's how you can see this layout here. And you can see metal to poly crossover here, that is possible. Only thing is, this poly and this poly, they are 2 different paths, they should not cross over. There will be a short circuit there. Here also you can see, we connect poly to poly here, we have to short gate to gate, and gate to drain also is shorted here. This is that IDC point. And you can see, we are taking poly over metal itself. So this way, the layout can be done. As I've been telling you, layout is an art, layout is a personal style also. And after this layout is done, its verification can be performed using Ashura, that is using Ashura DRC, RCX, LVS, DRC, LVS, RCX, layout versus schematic, design rule check, and RC extraction can be performed. After RC extraction, there is one more process called back annotation. That means the simulation or the verification of the layout by giving the input signals to the same. Now there are parasitics in the layout. Along with the parasitics, now the performance will be slightly degraded. But we will have to have a compromise with the degraded performance only now, because this is the one that is going to be manufactured in the foundry. This layout which is final, this layout's information can be transported to a file called GDSII, generic data stream for information interchange. It's also called as graphic data system for information interchange. Now that is going to be a database file. Generally they call it as a Gerber file. And the database file is going to be sent to the foundry to get the chip manufactured. So in general, in the industry they perform a back annotation process. Means after the layout is over, they will simulate it once again and they will find out the specifications after the layout. That is going to be the final specifications for the chip. If there are deviations, again they will have to work out on the circuit simulation once again to improvise on the performance. So with this, I have come to the end of today's lab class. If students have any doubts or queries or questions, you can ask me. Okay, I think nobody has any questions. So Deepak, can you listen to me?
Yes, sir.
Yeah. You can create one assignment in the Google class.
Yes, sir. I have created, sir.
Yeah. So students, you post your observation book of today's class into the Google class. I will be stopping the recording, but the meeting will be on. I will be stopping the sharing of this PDF also, but meeting will be on after you post your PDF in the Google class. You can exit from the meeting.